If you want. Okay, hello. Please introduce yourself.
Hi, I'm Andrej Bauer from the University of Ljubljana in Slovenia, the math department. And I'm here at the Unimath school. I'm one of the lecturers.
Yeah, tell us something about you. Yeah.
About my work?
Yeah,
Well,
about your work.
Okay,
About
so
you.
I've started my work. I studied at Carnegie Mellon University. I was a student of Dana Scott's, where I did computable topology and analysis, and then I also work on programming languages, constructive mathematics, and recently type theory, and also homotopy type theory.
Thank you. What pushed you to research and work in this area of Unimath?
I was always, already as a student, I was interested both in mathematics and in computers. And then when I got a chance to study both at the same time, that was a good opportunity for me, and it just felt natural. I was always interested in these topics of how to do mathematics with computers and what mathematics has to say about computing. So these are related topics. So how I ended up doing homotopy type theory and univalent mathematics? Well, around 2000, Steve Audi and I wrote a paper called Propositions as Bracket Types, where we had what is now known as propositional truncation in univalent mathematics, and then everybody told us, like, why are you doing this? This in extensional type theory, there's something called intentional type theory, you should do it there, and we did. We tried and we failed, and then later on, Steve Audi succeeded together with Michael Warren. They found the homotopy interpretation, and also Vladimir Voevodsky did it at roughly the same time independently. Anyway, because of my history of having done sort of the predecessor to this, I was always interested, and that's how I got involved in homotopy type theory.
Thank you. How do you think we can use Unimath in life?
In life?
Yeah.
You mean in mathematical life, I hope?
No, in
ordinary life?
Yeah, in ordinary life.
Well, okay, so it's a fair question. You can ask the same question almost about like any mathematics. You know, somebody says, "Oh, but how are we going to use number theory?" Or, "Oh, how are we going to use topology?" And I would say that maybe it's not immediately apparent how it's being used, or that it's, you know, if somebody invents a better vacuum cleaner, then everybody understands that this is useful because they now have a better vacuum cleaner. But when we're talking about mathematics, there often the ideas have a more lasting and profound influence on what happens in science and engineering, but maybe we can't really pinpoint to particular uses. Sometimes we can, sometimes we cannot. So I think Unimath and the developments in type theory, well, they have already had an enormous influence on how computer science is done, because they have a big influence on programming languages, and that's an important aspect of computer science. And then programming languages are important because, you know, all software is written in programming languages. So in a way, you're asking me, has software had any use in real life? And I think the answer there is obvious. So it's more, we really are talking about long-term foundations of things like software here, I think.
What is the future of Unimath?
So you're asking about Unimath. That you should actually ask the Unimath people, because they particularly work on the Unimath project, and they know better what the plans are. I was part of a similar project called the Hot Library, which is sort of a sister to this one. So I don't know. I think, so if I can offer my perspective both about the Unimath library and the Hot Library and other such developments, if you look at them, they are large. Their efforts to formalize a fairly large body of mathematics. If you look at Unimath, it has algebra and real numbers, and, category theory. It has homological algebra, it has lots of, relatively speaking, lots of mathematics has been formalized. It is a tiny bit of mathematics in comparison to all of mathematics that humanity does and knows, but it's at the same time maybe one of the larger ones. I mean, there are larger ones, there are still larger ones because they're older, like Mizar library, and I think these are sort of these will be remembered as the prehistoric attempts to do mathematics with computers. I think this is an important long-term goal. It was also a very important long-term goal of Vladimir Voevodsky's, was to do mathematics with computers so that we have the computer check that everything is okay. But we don't really know how to do it. And each one of these efforts, like the Unimath library, the Unimath project, is just a big effort to see how to do it, improve the methods, learn how to formalize mathematics, and figure out the way forward. Now, is this the right way? We don't know. That's why it's research, because we don't know. Will AlphaZero from Google come by and just learn overnight how to do mathematics, and that'll be the end of it, and we won't have to formalize everything? I don't know, maybe. But until we don't, because we don't know, we have to try different options. And type theory seems to be one of the more successful options so far, and within type theory, univalent mathematics offers a very good explanation of what is going on and how we should be doing mathematics with computers.
Yeah. Some people say that the mathematics is a kind of language. Is it true?
It's also a language, but it is also a way of thinking, because I think the two are connected. You cannot separate them. So it's definitely a language, which is even more obvious in something like foundations of mathematics. Foundations of mathematics, like univalent mathematics, are mostly about language, but they're also about the method, which is how do you use the language, and then they are also about how do you understand the language, and that's where the understanding means also the meaning of the language. And I think all of them have to come together. Mathematics is not just the language. That's just one aspect of it.
Mm-hmm. Okay. What many people love beautiful things. Is mathematics such a thing? Is mathematics beauty? What
yes,
is the
okay. So
beauty of mathematics?
If you go through, like, if you do mathematics in the primary school or in the high school, you cannot possibly understand why anybody would say that mathematics is beautiful, because it is horrible. And I agree. I think that the kind of mathematics that people see in school, if I can give an analogy, so suppose nobody ever played any Beethoven symphonies for you, but they showed you the notes and they told you that this is a beautiful piece of work, and you don't know how to play instruments, and you look at the notes and you have to memorize the notes. They force you to memorize the notes, and then maybe they make you sing a little bit. Well, are you really going to understand what it's going to sound like when an orchestra plays a Beethoven symphony? I don't think you have a chance. And it's a bit like that, right? Now, with the symphony, it's different. With the symphony, you can sit in the audience and you listen to the orchestra and you enjoy. But I don't see how you can do that with mathematics. With mathematics, you have to do it to enjoy it. You cannot just be a spectator to mathematics. It is the kind of beauty where you need to participate to experience it. Participate actively. You have to be able to do it to understand the beauty. And so that's why it's maybe a little more mysterious than other forms of beauty, that people find in art and in other areas of life.
Yeah. What you will say to teenagers that are thinking to learn mathematics?
Okay, so first of all, I don't think every teenager should play the violin, and not every teenager should be a professional gymnast, or right. And so everybody should find, hopefully everybody can find something that interests them. And if you're interested in mathematics and you're a little bit gifted, so you have a good basis for doing mathematics, you find it enjoyable and you find out you can actually do it, well then, go for it. Because maybe your parents will be worried about what you're going to do, but at least in my country and every country that I know, if you are a mathematician, it's very easy to get a job. It may be difficult to get a job as a professor at a university, but if you're interested in mathematics and you are willing or ready to do the kind of things that mathematics is used for, then it's very easy to do it, and you can have if you can be paid for doing what you love to do. So that's the best. That's a very good thing. Oh, maybe one thing to say is also this. Sometimes people have this impression that there is nothing new in mathematics, that mathematics has been all done. For instance, you study mathematics in school, and it's exactly the same as the mathematics that your parents studied in school. And so it looks like nothing, that mathematics has all been done. Nothing can be further from truth. So once you reach beyond university mathematics, you see that we know almost nothing, and there is lots and lots of open questions. Of course, a lot is known, which means that the things that are open questions and the new mathematics that's coming is maybe a little more difficult than it was 200 years ago. The tree is higher up. You have to climb more to get to the top branch. But once you're at the top branch, you're higher up, so you see more, and so it's a benefit. If you're thinking about doing mathematics, don't worry, we're not going to run out of it, ever.
Thank you.